So hi, I'm another David, and I'm working with the other David. So I'm going to give another research talk in the first part of this class about detecting planets, which you've already heard a little from Eric and Becky. And then in the second part, we're going to do a bit of look over some Gaussian process code and just some simple illustrations just to get familiar with actually using Gaussian processes in practice. So yeah, I don't imagine we're going to go all the way to 7 p.m., but we'll see. Okay, so let me begin. So the title of this talk is Detecting Planets Jointly Modeling Radial Velocity and Stellar Activity Time Series. And I have a subtitle which is Using GPs to Find EPs. So GPs are obviously Gaussian processes, and EPs are exoplanets. And as I said, this is work with David Stenning and Eric Ford, who you saw here before, and others. So you may have heard in the news recently detection of some exoplanets, this TREPHIS 1. So 7 or more planets were found around the star, Earth-like planets, in fact. And they're Earth-like. In particular, some of the planets may have liquid water on them, which is why they're particularly interesting. Yeah, so then the question is, I think it's these middle ones that may have water. So then the question is, like, why not just kind of fly off there? Why do we keep looking for planets? And so I think you probably saw this plot from Becky Dawson, but here's the planet mass in log scale. And also relative to the Earth mass, right? And then orbital period, also in log scale. And these blue dots are kind of what we've detected, right? You can find this on exoplanets.org. So if you want to play around with, and if you click on each planet, it tells you how it is detected and so on. So that's fun. And you can see that planets that we might be interested in, we couldn't actually detect. Or it's very unlikely that we will detect these at this point. So people are interested in studying the population of planets, how many Earth-like planets, how many Jupiter-like planets, and so on. So in order to do that, we need to kind of get better at detecting this type of planet, assuming there are other Earth kind of sized planets, but we imagine there are. And one of the things we need to do in order to be able to do that is to deal with stellar activity, so that a star isn't just like a constant light. Instead, various things go on the star. It changes, like some parts are dark and some parts are lighter, and various things go on. And when we're trying to detect very small signals, that gets in the way of us being able to see the planet signals. So I'll try to, and that's what I'm going to kind of talk about. So before I get to that, these are the two main ways of detecting planets, which maybe you heard a little about before. The first one is the transit method. So the planet passes in front of the star, and the star's light kind of dips. So that's what's happening here. And that's very good for, say, working out the radius of the planet, because you can kind of tell the amount of light that was blocked, so you can work out the radius. And then the second method, which is the one we're going to talk about, is the radial velocity method. So here, the star is kind of moving because of the planet going around it, the gravitational force of the planet. And sometimes the star is moving towards us, and then the light looks bluer, and sometimes it's moving away, and then the light looks redder because of the Doppler shift, right? And so by detecting that effect, we can tell that there's a planet there. And the other thing we can tell from here, which we can't tell as well from that method, is we can tell the mass of the planet because of the amount the star moves. Okay, so I have, because we're going to focus on that, I have a little video to illustrate that, if I can get out of my presentation. So This is a video from the NASA website. You can find all of our planets. So again, this is just the planet going around the star. Sometimes the star is going away, and then the light is redshifted. And sometimes the star is coming towards us, and then it's blue shifted. Right? And obviously it's kind of periodic, so we get a repeated signal. Okay. So I guess I'll just end that. And so this is the type of signal we get. I should maximize this. I'm going to play another thing. So the type of signal we get. So this is the y-axis is in meters per second, and it's the velocity that the star is moving away from us, so up to 50 meters per second or so away from us, and then negative is towards us, so some up to minus 50 meters per second. And this signal is from the 51 Pegasi detection, which was the first planet to be detected around a main sequence star. And it's a very, very big signal. Okay, I think maybe Eric Feilsen mentioned this, but so this planet is about half the size of Jupiter, and its orbit is 4.2 days. So it's almost inside the star. So it's very, very close to the star. So there's a lot of gravitational effect. So the signal is very large. And so for many planets, the signal is going to be smaller. And there's also going to be other things mixed in with this that's making it more noisy. And that's the stellar activity that's going to make this harder. Okay, so I have another video to illustrate what kind of things stellar activity might be. So we might have dark spots on the star, like this. And so the reason that's an issue is that the one side of the star, this side, is moving towards us, and the other side is moving away. Right? So the side that's moving towards us, that light is blue shifted, and the side that's moving away, that light is red shifted. But it kind of cancels out because it's the same, right? One side has to go as the other one comes. And so what happens is that, I guess that should play, is as the dark part comes around the spot, it blocks some of the light from that side. So then there becomes an imbalance of this blue and red shift just from the star rotating. And so then it appears that there's a radial velocity signal. The star is moving because of this apparent shift, either blue shift or red shift. And so then we think that the star is kind of moving around in an orbit when actually it's just spinning. Yeah. So that's where the radial velocity corruption comes from. So that was this. And so we get this corruption, and corruption, of course, is bad. So this is kind of the ideal planet signal that we would want. And then if there's a single spot on the star, it could create this type of signal. And the signal can even be bigger than the signal for the planet. So the y-axis here is in apparent meters per second. So it's the apparent radial velocity of the star, just due to the spot. And so the final thing we could actually observe is this, where it's mixed in. And so what we would like to do is kind of work out what this is and subtract it out so that we can get the planet signal. Right? But in practice, that can be challenging. One, the planet signals can be very small. So for an Earth-like planet, less than 1 meters per second. So the one I showed you before, the 51 Pegasi detection, was over 50 meters per second. For an Earth-like planet, it would be less than 1 meter per second. In fact, much less, like 13 centimeters per second. And as I think Eric Feilsen emphasize that's much slower than walking speed, which is like 1.4 meters per second. So it's kind of amazing that we're even thinking about detecting these things just such small velocities so far away. And another issue is that, of course, I've just said one spot on the star, but there could be many spots on the star. There are also plaques, which are like bright inverse spots, basically, bright parts, and various magnetic things going on as well. So it can be very complicated, and also you can have highly irregular sampling. So what we would like to do is kind of stop the corruption, okay? So what we actually observe is that at different time points we observe the entire spectrum of the star that's recorded, the star's light. So at different wavelengths we have all the different. So we have this huge, you can think of it as like high-dimensional data, right? And all the radial velocity does, that when we get that time series, that radial velocity time series, is the entire spectrum moves. So from time 1 to time 2, the spectrum moves if there's a planet. And so it just from left to right, so it shifts, and that's what this bottom one is illustrating. And then we get this time series. But we could have done lots of other things with the spectrum, because also there are many different changes, many other changes, not just a shift. If there's a spot on the star, lots of things happen to the spectrum, not just this shift. And so the statistical opportunity is to use that other information to figure out what the stellar activity is and then remove it and just recover the planet signal. Okay, so that's actually what the kind of state of the art is trying to do. So there's this recent approach by Rajpal et al., 2015. They have, there's no planet here at the moment, okay? There's just a spot on the star. And this is like simple simulated data, but it's fairly realistic in some sense. If there was a single spot on the star, it would look like this. That's what I mean by realistic. So this is the apparent radial velocity, the apparent movement of the star due to the spot. Okay, so the star's not really moving, it's just rotating. But it appears to be moving. And so there's like 8 meters per second one way, and I guess it should be it goes down to 6 meters per second, I guess, because it's elliptical orbit. So, well, actually, yeah, it doesn't matter. It doesn't have to follow like a planet, but anyway. And then there are as I said, there are other things that happen to the spectrum, not just the shift. And based on those things, like the absorption lines, so there's lots of like lines here where there's various elements going on. I'm not going to go into the details of spectrums, but basically those lines could get deeper or shallower or wider or thinner or become asymmetric or something. And from that kind of thing, you can create other time series. And that can tell you that there's probably a spot. And in particular, you see these proxies are very nice because they're very related to the apparent radial velocity. So like the apparent radial velocity is kind of like the derivative of this, and it's almost the negative of this. So what would happen in practice is a planet would be mixed in here, but you would use these to figure out what this signal was. You'd subtract this out, and you'd just be left with the planet signal. Okay? And so this is, like, as I say, kind of the state of the art, but there's still some improvements that could be made, because this line is the kind of GP fit. So yeah, what I guess I forgot to mention is the whole model, the way they model this is by a big Gaussian process. So these are modeled as 3 dependent Gaussian processes, which is why I'm talking about it right now, because we've been talking about Gaussian processes. So I'm going to go a bit more into the details of that, but their model is not completely ideal because it kind of misses some of the points, so it's not fitting the data very well. So, and the other thing is that, as I said, astronomers are very keen to understand like these simple situations where there's, say, a spot on the star, or maybe a couple of spots. But the real data actually looks like this. So it's kind of, that's why they're using Gaussian process, because the Gaussian process is very flexible, so it can kind of capture this, it can adapt to this kind of situation. Whereas if you just said, okay, the previous slide looks kind of like a sine function, I'll just use that. When you were hit by the real data, you would die. So yeah, that's why we're kind of using Gaussian process. Okay. So now I'm going to kind of go on to some things that we've been doing. But are there any questions like so far about things that? Okay, so in our kind of work here at SAMSI, some of our goals have been to find more informative proxies for the star activity. So as I said, some of the lines get deeper or wider or something. And basically some people have picked out, on the previous slide you saw some proxies, like proxy 1 and proxy 2 as I was calling them. And those are just kind of things that people have picked out and said, this seems like, it's important. But can we somehow pick out the best proxies in some sense? And so we've been doing that, particularly David Stenning. And then also we're trying to make the model more flexible, because if we get different proxies, we need different models and so on. And then we want some way of choosing the best model. So I'll begin by talking about how we construct these proxies. So as I said, we're just going to focus on the case where there's a spot. There's no planets yet. There will be planets in the end, but no planets yet. And there's some very nice software for simulating what you expect to get when there's a spot on the star. It's called the SOAP 2.0, the Spot Oscillation and Planet 2.0 Radial Velocity Simulation Software. So it simulates the kind of radial velocity you expect for spots on stars. And we're just going to consider the simple case like Rajpool did, the Rajpool et al. Paper. We're just going to have one spot on the star, and there's some parameters we have to set, like the inclination of the star relative to the Earth and the position of the spot on the star. But we're just going to fix those for now. And then, as I said, we're going to observe the star at different time points. And every time we observe the star, we're going to see this, like a spectrum. So lots of data. And in fact, we have 237,000 wavelengths of light in the spectrum. Okay. So then, as I mentioned, this is the kind of zoom in of the spectrum. So all kinds of things happen. So the blue is just like the normal spectrum. So perhaps when the spot was behind the star, you just see the normal blank star, if you like. And the red is when the spot is like going across the front of the star. And so all kinds of things happen. So this line, which becomes shallower, I was trying to find the word. This one becomes slightly deeper. This one becomes wider. And there's all kinds of stuff going on up here, right? So maybe that tells us that there's a spot. Who knows, right? So how can we get at that information in the spectrum? So this is our data. Our data can be written as a spectrum at each time point. And then a recent paper has used PCA to kind of do dimension reduction. So are you familiar with PCA? Yeah, sort of. So it's I'll just very briefly say. So this is your like data matrix, and then you can. So basically, you want to express it in a coordinate system where you don't need like. So it's n times p. So here p is 237,000. So all the wavelengths. So we don't really we only have 25 data points. We don't really want to express each data point in terms of 237,000. So instead, what we can do is, so you can, so if you were to kind of change coordinates, basically, then this, you can do that by constructing this matrix W, and it's basically based on the eigenvalues of xtx. And if, so the eigenvalues of, eigenvectors are placed in order of how important they are. And if you want to reduce the number of dimension, you just write, you just cut out some of the columns, basically, of the matrix. And so you now have a M by L matrix. So yeah, it's just a dimension reduction technique. Yeah. So you'll see some plots which will make it maybe easier. Yeah. But we use a kind of a variation on that. Instead of just applying PCA, we instead, we know that there's going to be this radial velocity component, and we're interested in recovering that. So we're just going to fix that to be our first component, our first vector. And then the other ones we're going to run normal PCA on. So I think if I just show the plot, it will become a bit clearer. So our spectra, our data can be expressed like this. So there's some part that's the apparent radial velocity. So this is actually in meters per second due to the spot. And as the spot phase changes, then this signal changes. So sometimes the spot is behind the star, and then there's no apparent radial velocity. And then there's some other things going on. And yeah, and these perhaps correspond to some deepening of lines or something, but it's but the point is that what PCA does is it finds the directions of maximum variation in the data, and so this tells us kind of the maximum information that we can extract in a single direction and then another direction. So this is basically a new coordinate system. But anyway, so the task that we have, moving away from the details of PCA, the task is to say this radial velocity signal is going to be mixed in with a planet signal. And we want to try to recover that from the other signals that we have extracted. So this is like proxy 1, this is proxy 2, and then some other things. So these actually look very similar to the Raj-Paul et al. Signals. So this is the signals they had, and you'll see that our signals are kind of similar. Okay. But you can also do things other than PCA. So there's this thing called diffusion maps. So PCA has a linear constraint. But it basically, so the point is that if you had some complicated structure like this, so this is a spiral, then PCA, if you try to apply PCA to reduce the dimension to 1, I guess, then it would be like drawing a line across here and then projecting onto that line. And that would just destroy the spiral. Okay? So we'd rather not do that. What diffusion maps does is it says, we can set up some diffusion. So basically you start somewhere and then over time you diffuse to nearby points, okay? And then you are essentially projecting to a space where the Euclidean the normal distance is just the diffusion distance in this space. So for example, this point where it's blue is going to be very far from somewhere on the other arm of the spiral, because to get to that point you'd have to go all the way around the spiral, right? So basically it's just a way to deal with non-linearities in your data. So it could, if you to illustrate what it's doing, if you just parameterize this as saying like this is point 0, and then as you go along it's like you go all the way to 1, you just parameterize the spiral, right? So here's the spiral parameter, and here's the first diffusion map coordinate. You can see that they're kind of very closely related. So when you transfer to the diffusion map space, you're kind of preserving this spiral structure even in the first coordinate. So it's not just projecting onto a line, it's preserving somehow this spiral. So anyway, you can do that and you can get out different signals, but they're somewhat similar. So again, the first one is just the normal radial velocity signal, and the other two are different. Okay, so what we want to do is we want to model, say, 3 of these signals as a Gaussian process, a joint Gaussian process. And so we're going to have some rules for the models. So they have to be flexible. So they have to be able to capture these different signals. So I showed you the Raj-Paul model was kind of a bit off sometimes. And also, we mustn't eat the planet. So what this means is that, say this is the radial velocity, the apparent radial velocity. So this is the effect of a spot and a planet. And if our, so the planet signal is kind of this bit that peaks up here. If our model just fit this, then we would be saying that our model for the stellar activity could fit even if there was a planet in. And so it's kind of, then we wouldn't know there was a planet, right? We'd rather there were some residuals after we fit the stellar activity. So we'd rather, in some way, we'd rather this kind of thing where, because there's a planet signal in there, it says I just can't fit this, right? And then you would see the large residuals, and you'd know there was a planet, or hopefully. So.
Yeah. So the goal is not to make a best fit. Well, because if you have best fit, then that explains the variation of the planet signal.
Yes. So.
But then, how do you force not to have the best fit?
By not putting too many parameters in the model. Right.
Okay, but is it possible to determine just one of that models? Because there can be many non-best parameters. If we try to have the best fit model, there must be 1 or 2 or 3. But if our goal is to find second best or third best models, and there are possibly.
No, so what we try to do is we try to get so we try to find the best one for modeling the stellar activity, but without a planet.
And that automatically guarantees the second picture?
No, not automatically. So we hope that it guarantees that, but we do a test to find out if it does that, and if not, we go to the next one, kind of thing, right? So we'd start with the model that's best for capturing the stellar activity, and then if we then try out in some simulations whether it's useful for detecting planets, whether it does this or this, And if it does this, then we say, okay, that model is has too many parameters. Let's get rid of some of them. So move to the next best fitting stellar activity model on our list, and then check again whether this happens. Okay, and I'll kind of talk through that process.
And right here, this is only one feature as well.
Yeah.
So the model itself includes a Gaussian process and its derivative. So by fitting to the other features, you can't always make it too flexible to just this first one.
Yeah, you'll see that there are multiple outputs.
Yeah,
it will become clearer. Yeah. So let's just review the details of Gaussian process again. So as you heard several times now, I guess, Gaussian process can just be viewed as a stochastic process. You observe it at some times t1 through tm, and then this vector of observations x of t1 through x of tm, that follows a multivariate normal distribution. So in our case, the radial velocity time series could be said to follow a multivariate normal distribution, okay, with some matrix sigma. And obviously, what that matrix is important. Otherwise, this is just a very non-interesting model. So typically, people parameterize this covariance matrix, such as this is saying the covariance between the process at time t and at time s follows this form. And this form only depends on the difference in time between t and s. Okay. And so this is again is just a review from the other week. So it's maybe surprising in some way, but so Gaussian process just exploit the multivariate normal distribution properties, which makes things very flexible. So imagine that that you wanted to know the process at times t1, and you had observed it at times t2. Then a Gaussian process would just be like set up this. So you have a vector of observations, some of them, well, you have a vector of times of the process, and some of these times the process has been observed and sometimes it hasn't. And then you define your covariance matrix, and then you can predict the process at times t1 from your observations, just following the multivariate normal calculation. So this is basically just a regression, because you just have your observed times, x of t2, and then some linear combination of those. So it's just like a regression, basically. Okay. And so that's what's going on. So when I show some plots, and there's going to be some observations and then some red lines, and the red lines are determined using this. Okay. So I'm just basically doing a regression, filling in them. So before I get there, I just want to show the details of this Raj-Paul et al. Model. So again, they have three signals. The first one is the apparent radial velocity. The second one is the first proxy for the stellar activity. And the third one is the second proxy for the stellar activity. So the radial velocity is modeled as a Gaussian process. This is xt. And the derivative of the Gaussian process. So this is kind of a slightly, I guess people don't use the derivative very often. So that's sort of a slightly different feature of this model. And they have some kind of vague physical argument for why they should include that. But it works. It seems to work reasonably well as well. And then they have some stellar activity proxy. This one is something to do with there's two absorption lines to do with calcium and their relative width. This is what this stellar activity proxy is. And they say that's just modeled as a Gaussian process. And then there's this other stellar activity proxy, which is something to do with the asymmetry of some of the lines, the absorption lines in the spectrum. And that's modeled as the Gaussian process and its derivative. And then they have this kernel that they use to define the Gaussian process. and it has a periodic part that involves a sign, so they expect periodic signals because the spot keeps going around the star, as in these signals. And then another part because in reality, the spot on the star is going to change shape and die away and then come back and so on. So you want some term that kind of damps the periodic part. Okay. Yep.
Is there any way you assume a parametric model and then end up with this covariance function, or you just putting this before considering any parametric model on your observation?
Yeah, so we're not considering a parametric model. We're just using the covariance structure.
Okay, see, this is just kind of empirical way to estimate the covariance.
So yeah, so it's a non-parametric technique. That's the Gaussian process.
Yeah, I'm wondering, is there any way to do the reverse, or you have this one and end up with parametric model?
You can combine both. Were you here last week? So last week I showed that you can have a parametric model and then a Gaussian process kind of models the noise, the residuals. But that's not what David is doing here, because there is no parametric model that we kind of want to assume for this.
Yes.
But if you have a physical model, that can be incorporated into a general approach that involves these Gaussian processes for acknowledging correlated errors.
Yeah, so one thing is, as you were saying, like you could say like your sine curve here, right? And then sometimes,
Yeah,
but then
I can get it that you're trying to predict the covariance structure based on your series, right? But not any parametric model. So is there any way we can put any parameter model on X's and end up with this covariance matrix?
So you would put the model on the x's.
Yeah.
It would be on whatever the output is. So your x's are actually.
you do on the mean of X, usually,
Yeah.
right? So usually the way it would usually work
X's
is,
are the series, right?
sorry?
X's are the series.
Yeah,
right?
sorry, I was getting confused between my notation from last week and this. Sorry.
So usually, so we have the radial velocity time series. We're just saying it follows like a multivariate normal, or just a normal distribution, right? All three signals follow the normal distribution with just mean 0, right? But if you say, well, I kind of know what shape I expect, you could put that in for the mean instead. You could put a parametric model in for the mean, and that would kind of capture the basic shape. And then,
But the mean won't appear on the covariance structure.
no, it won't.
Yeah. Okay.
Yeah.
Yeah. Thank you.
Yeah, so people also use like basis models, where you can model both the mean and the covariance using basis functions. Yeah, so they're kind of like non-parametric. They're also non-parametric, but it's you're using basis functions. Yeah. Okay, so again, so their model is just these three outputs follow a normal distribution. And a normal distribution looks something like that, where the first row corresponds to the radial velocity time series, and the first column involves terms. Either this one is just the kind of, if you were just to fit the radial velocity time series by itself, you would just have that sigma 1, 1. And these are like the cross terms, like sigma 2, 1, and so on, right? And yeah, it turns out that it's fairly straightforward to compute this. You just, if you want the covariance between a Gaussian process and its derivative, you just take the derivative of the kernel function that we defined. So that's actually very nice. Okay, so these are the plots I was talking about. So our signal our proxies, so this is the first output that we have, so that's just the radial velocity, apparent radial velocity due to the spot on the star. And these are our two proxies that we got from our kind of PCA way. And we're just going to fit the Rajpal et al. Model directly to our output. So there's no reason that it should really work for our proxies, our stellar activity proxies, because they're not the same as their ones. But they have a similar shape, so we thought it might work. And it does do a reasonable job, but again, it kind of misses some of the points in the trough or the peak, and we'd prefer that not to happen. This log likelihood is just because I was finding the MLE, so I was maximizing. So the red line is just like the MLE fit for the mean of the mean, and then there's also an uncertainty region, but the uncertainties are very small because the standard errors on these time series are on these observations are very small. Okay, so each observation has an uncertainty associated with it, and those uncertainties are very small in this one, which means that because the problem is all three of these, in this model, all three of these time series are tied together, because we're using like the Gaussian process in all three of them, so they're all tied up, and also the derivatives. So if we know if we know the Gaussian process, we kind of know all the outputs, right? So that's what's happening. And so the other problem with the model is that if we use our other proxies, which are the diffusion map, it just doesn't fit here, because this third one has some like up and down motion. It has two dips instead of just like the one as here. So this model can't fit it. Yeah, there's some other issues due to the fact that this is a very constrained model, and it has very strong negative correlation. So if you remove some of the data, you can see that the model is like filling in this area. The gray regions indicates the uncertainty for this mean fit. And because the process was very low here, it then says, oh, it should go up because there's a negative correlation. But that doesn't really make sense in this context. So we'd like to fix that. And this is just a plot of the big covariance matrix illustrating these negative correlations. So I've only plotted negative values. So in the second output, it just uses the Gaussian process, the xt. So there are no negative values because the covariance function doesn't allow negative values. But when we look at the covariance between the Gaussian process and its derivative, we can have very strong negative values in the covariance function. So that's why we're getting these kind of, it's because it's gone down, it then says it has to go up, which is not necessarily true. So we tried to kind of address these problems, and we tried lots of things, but the two that worked were to add in a second derivative of the Gaussian process, and also to add in an independent GP, so you have an additional GP to kind of capture some correlated noise. So I'll try to just explain those in terms of these. So this last output is turns out to be kind of like the second derivative of this. So this one is kind of like the derivative of this one, and this one should be kind of like the second derivative of this one. So if we add in the second derivative into the model, it will help.
Why should they be derivatives of each other?
They shouldn't necessarily, but they just are.
Just you're saying by the shape of the function?
Yes. Yeah.
Oh,
Exactly.
So you're like drawing like inference?
Yeah, basically, yeah. And there's
is there any like intuitive meaning like why that would happen? Like, it has to be pretty
So interesting.
Yeah, it is kind of interesting. So they, so Raj Fullerdale had some reason why their outputs look like this. So this one is like the derivative of the second one, and so they set up their Gaussian process to be the square of the area of the spot as a proportion of the area of the star. That was their interpretation of what xt was, and then I guess the derivative may come in because it depends like where the spot is on the star. So when it's on the edge, it has a different effect to when it's in the middle, and so on. So I'm not really sure, but that may be where it comes in, and then I guess you can just keep extending that to second derivative and so on. Yeah, but yeah, I don't have any proper physical interpretation.
I mean, how these three series are related in terms of observing them?
So they're all derived from the spectrum, right?
Okay.
So the first one is the apparent radial velocity. So that's when the spectrum shifts as the star is moving away or moving towards us.
All are extracting from this one series, or?
They're all extracted from the spectrum, which a spectrum. So I showed you before that.
Yeah, I think I missed that part.
Yeah. So the spectrum is just like this. So at each time point we observe this. So it's the light broken into different wavelengths. So it's very high dimensional. So this is 237,000 wavelengths recorded. So at each time we observe that, and if you just observe the first output, you've reduced this whole thing to just one point on your time series.
Okay,
and then the other, so this, I think I showed a section. So the radial velocity time series is just the shift of the spectrum. So this is just an illustration of the spectrum shifting. But the spectrum does other things as well. Like some of the lines change height, and then that gives the other time series. Yeah. So basically, if you were to just look at the spectrum, it's very difficult to say what's happening with it. So that's why we've done some kind of dimension reduction like the PCA or something, and then just got some time series out instead of looking at the entire spectrum, which would be difficult. How are we doing for time? Okay. So anyway, we started with a general model that looks like this. So we just extended the model to include the second derivative, and also this independent term to help model correlated noise. And we're not going to use all of these terms. Some of these little a's, these coefficients, are going to be zeros. Okay, but well, this is just the general model, and then we're going to select the best ones within this. Okay, and yeah, I guess that's all I want to say about that. Okay, so how will we select the best model from this? So we did 3 steps. This kind of comes back to tax question. So the first step is to say, what's the best model in this class for modeling our stellar activity? So we have the spot on the star, and we have our 3 outputs. What's the best model for that? And we use these criterion, basically looking at the value of the likelihood, the maximum likelihood value, and well, I guess it's like the chi-squared value, and then and we also do cross validation there. But then, as we kind of alluded to before, that might not be the best model for what we're trying to do. What we're trying to do is find planets. So so what we want to do is a hypothesis test where we say the null is that our stellar activity model fits the data, so we're fine. The alternative is that it's not good enough because there's a planet signal. So there's a planet, right? And so we kind of try out our models for doing that kind of test.
So each model is just a different number of the A coefficients, maybe 0 or not 0?
Yes. Yeah,
what is the dimension of the A? So
A is just a scalar. Yeah.
Oh, but if you take all the coefficients and you like were to think of it just as a matrix.
Yes.
Well, like, because it's like how many observed time points do you have? I guess.
So, time points.
Yeah. That you've observed.
So I'm just observing maybe 100 time points in the 3 outputs, but it could be more. Yeah. But the A's, there's 12 A's, I guess, right? Because but the A is fixed across time. Right? It's only the process that changes.
So these are all of the parameters that
Yeah.
to
Yeah.
select from.
Yeah, all of the parameters and the parameters in the covariance matrix. That's it. Yeah. Okay.
So it is possible then to look at like the AIC or BIC for all models?
Yes.
Okay.
That's what we're gonna do.
Yeah,
Yeah. 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 Okay. Yeah. And then there's some. In practice, we're going to do something. When we've chosen the best model, we're just saying we're sticking with that. We're going to do something slightly different. We're going to. So the BIC and AIC and stuff, that's an approximation to other things. And one of them is the Bayes factor. And we're going to calculate the real Bayes factor in practice, because we don't want to base saying we found a planet and then we used some approximation that wasn't very good. Okay, so this is exactly a comparison you asked about. So the definition of the BIC is this. So the log likelihood, as I said, is a bit like the chi-squared thing. And then this first term is a penalty. So m is like the number of parameters, and n is the number of data points. Okay, so that's penalizing the number of parameters. So you don't want too many parameters unless your likelihood is getting better. So smaller values of the BIC are better. And we also do some cross-validation, which is where you leave out some points and see how well you predict them. Okay. So all the possible models turned out to be 3,375, and for our stellar activity proxies, the Raj pool model was the 2,200 and something best BIC model, right? So if we just look at the BIC criterion, it's the 2,000th best model. And then there's some other model we tried in the second row of the table, and then the third and fourth row are the best models according to these criteria for choosing models, this AIC and BIC. And I'm focusing on the BIC. So you see the AIC and BIC values are smallest for these two models, and also the cross-validation is, so the optimal value for cross-validation is -46, and these two got -45, so close to it. So what are those models? So this is the optimal BIC and AIC model, which turned out to be the same in this, if you're familiar with AIC, which I haven't really mentioned. So the first output is modeled by the Gaussian process, x, with some coefficient, 0.01, and also the derivative of the Gaussian process. And then the others that are left out are 0. Okay? So they were ignored. And then the second output is modeled by the Gaussian process, x, and its second derivative. And the third output is just modeled by the derivative. And these are the estimates for the parameters of the covariance matrix. So the real, so the spot goes around the star every stellar rotation, and the stellar rotation is 10 days here. And so the estimated period is log, well, the log period is 2.3, that's the estimated period, which is 10 if you exponentiate, so that's good. And these are dictating which part, whether the periodic part or the decaying or the non-periodic part are more important. And smaller values mean, because it's this length scale term, so smaller values mean that it's more important. So basically the periodic part is important and the non-periodic part is not, which makes sense because it's periodic, right?
What does joint mean?
So joint means, so what I mean there is that these coefficients are used in all of these models because they're used for x. This is the covariance matrix for x. So these parameters are shared across each output because x is in each output. It's just because I mentioned before that I might that we were allowing to add in an independent component, and that would have different parameters. So, as I said, this is the testing problem I mentioned. So we've selected our best model. Is it good for finding planets? So the null, we're just going to do a hypothesis test. So the null is there's no planet, which means that our stellar activity model is great. So then the first output might look like that, see? The second is the first output also has a planet in it. There's a planet, so the planet is contributing to the radial velocity, and our first output might look like that. That's the ideal case, because our stellar activity model doesn't fit if there's a planet. So we need to add in a planet model as well as the stellar activity model. So fortunately, how a planet, as that picture at the beginning, the star goes either towards us or away from us, and that causes the, and that's what the radial velocity is. And the signal the planet causes is very well understood. And so I'm not going to go through these details, but basically this is the radial velocity due to the planet, okay? So people understand how that works, and this is a good model. And so the only things that are important here are k, which is the amplitude of the signal, and tau, which is the orbital period of the planet, so when the signal repeats, okay? So what we're going to do is we're going to simulate some data sets without a planet, and then run our model with the planet. Run the model just of the stellar activity, and then run the model with the stellar activity and the planet model together, right? And for both of them, we're going to calculate the BIC, which is this. Sorry, this should be log n. But anyway, the BIC is basically saying how well we're fitting it, and the difference in BIC is the estimate of the Bayes factor, and the Bayes factor tells us which model is preferred, right? Which model is doing better. So what this is doing is it's saying, suppose we have data sets without models, without planets, and then we do this, then we find how much it's going to prefer the model with the planet. And so for larger BIC, it means it's have greater preference for the model with the planet, okay? So this is the null distribution, the distribution of delta BIC under the null that there's no planet. And so if there was a planet, we would hope that there would be more evidence that the model with the planet was good. So we'd hope we'd have a larger value of delta BIC. So this red line is the 99% quantile of the distribution, and we want it to be so if there was a planet, we'd hope that delta BIC was larger than that value, so we could.
How do you generate the data?
So
from the null distribution? Yes.
So we have that simulation software for that SOAP 2.0 I mentioned ages ago. So we have that, yeah. So that's nice because it simulates real stuff, but it's actually based on spectra from the sun, sorry, and so they're real spectra. The only thing is that we are assuming kind of a constant size spot and things like this, whereas in fact this would need to work for a variety of sizes of spot and so on. So we're kind of fixing some things which we wouldn't be fixed necessarily. We wouldn't know that was the case. So there are some limitations to this, yeah. And so here's a summary of the results. So next, we simulated data sets with planets in them. 50 data sets in each of these squares, which I'll explain in a second. And the planets have different amplitudes of the signal. So from 0.1 meters per second, which is a very small signal, radial velocity signal, to 2 meters per second, which is still small, but not that small. And then the period ranged from 5 days to 9 days. And the stellar period was 10 days for comparison. So what the first line says, what this table shows is the median BIC value. So if we look at the previous page, our cutoff is about 32, whatever BIC is, right? Delta BIC needs to be about 32 to reject the null. And this is the median value across my 50 simulations which haven't actually completed because we're doing some things. But so in the first row, when the planet signal is very small, it's 0.1 meters per second, the delta Bic values are not very big. And so our average power across these different periods, which are the columns, is only 2%. So we're not going to detect the planet then. When the signal gets bigger, we gradually do better and better. And you see by k equals 0.5, we're at 45, 75, 71, 63. So these values are all bigger than our cutoff of 32. So most of the time we're rejecting the null and saying there's a planet. And by the time we get to k equals 2 meters per second, we basically always find the planet. Okay, so that's good. I've put the biohazard symbol. This is one of my professors who likes to give this as a warning, and I'm using it here because these are kind of preliminary results. So don't fly to any of the planets yet because they might not be there. And then one thing we can do just to check that things are working well and so on is we can look at the parameters estimated. So the estimated value of k and the estimated value of tau. So the amplitude and the period of the planet. So when the signal is very small, we really have no idea about these parameters. And then as the signal increases, we gradually pin them down more and more. So by the time we get to the signal of k equals 2 meters per second, we have a pretty good idea of the amplitude of the planet. Sorry, I maybe didn't go over my plots clearly enough, but the first row is the estimates for the amplitude, and the second row is for the periods, and the different columns are the different periods. By the time we get to a large signal, then we're pinning down these parameters well. The only place we're not doing well is this, where the period is 5, and that's because the stellar period is 10, so you get confused between the planet and the star, because the spot comes around every 10 days and the planet every 5 days, and then it's easy to confuse them. And that's a common problem, like this aliasing, as it's called, of period. Period estimation can be very tricky because of that. So basically we can't do anything about that, realistically. Yeah, okay, so I guess I'm just about going to wrap up in a minute. We also tried some things for the diffusion map scores that, remember, have this kind of second derivative term. The Bic optimal model actually was too flexible, so we ate the planet. So that was bad, bless you. So we're kind of working on another model that cuts out some parameters, and so it's less flexible. This is the best one so far. So then just to kind of wrap up, so what I've talked about is that we have we've come up with some new stellar activity proxies by doing dimension reduction techniques on the spectrum that we observed. And then we've talked about these class of models and trying to choose the best one based on this criterion of we're trying to detect a planet, which is what we're really trying to do. And as we've kind of mentioned as we've gone through, there's lots of other points we need to think about, such as if you change the latitude of the spot on the star, or you change the inclination of the star, the kind of signal you get changes. So will it still work in that case? I mean, we expect, you can see the signals are still similar, so we kind of expect it will work, but we need to do more testing. And then there's kind of evolving activity and so on as well. So this is just an illustration of, this is an evolving spot. We try to increase the amplitude and then decrease it in a very simple way. And our model still is kind of fitting okay. So that's kind of an illustration of where we were hoping, by using the Gaussian process rather than a fixed model, we're hoping that it can be flexible to these kind of things. Was there a question? Oh, sorry, I thought you had your hand. Yeah.
Why the number is?
Oh, that number is in red because previously, when it wasn't changing amplitude, only the periodic part was important. The length scale for the periodic part was small, but for the exponential part, it was very large because the exponential part was ignored. But now it's not like strictly periodic because it's changing amplitude. Then the exponential part is becoming more important. So it's become smaller. Yeah. Okay, so I guess we should have a break now. One thing I just want, so afterwards we're going to look at the code I sent around, just briefly. And I wanted to just mention that if you could, there's some packages that you need. If you, I mean, you can just follow along if you want. But if you want to kind of run it on your computer at the same time, you may want to just run this first line to install any packages that you don't have, because I forgot to mention that. And I don't know how quick the internet is going to be for you. Okay. Okay, so I guess we should come back in, say, let's say at 5 to 6. We're just going to go over this code for some GP examples. So this first one is just some very simple examples. Just want you to see the covariance matrix and things like that. And then I'll show one on very similar code on some light curves, modeling light curves, periodic light curves. And then I'll finish by showing how this is implemented in STAN, which you may be familiar with or not. So this first code, I think TAC actually kind of edited from this person's website. James, I'm not quite sure how you say that, Kirsted, I guess. And so the first thing is just to load in some libraries. I guess most notably, I want to do that. This ggplot, which is just for plotting, and then gpfit, which is the R Gaussian process package. It's not very good, but the Python options are actually better. But that's one of the reasons why we're showing it coded in R, because you can't really use the package that much. And then fields is just for some plotting thing as well. So what we're going to do is set some times at which we want to predict the value of a process. So that's just xpred. And then we're going to set up the covariance matrix. So the covariance function we're using is just this squared exponential one. So just the distance between the two points, and then this denominator. So this is called the length scale. So as we saw before, if this is so if this is smaller, then yeah. So if the length scale is longer, then it should be smoother, right? Yeah, it will be smoother, because then even if it's well, anyway, we can change it and you'll see. So the length scale here is set to 1. Okay. So what we're doing here is we're constructing the covariance matrix. So for every point, we're calculating this covariance. And so we have this, basically what this covariance matrix is saying is that if you're nearby to the point, it's very correlated. Otherwise, it's almost 0, the correlation. So this is the big covariance matrix, right? And if you change the length scale, so let's say the length scale is 2, and do it again, then you see that you're correlated with points that are further away, right? So this length scale is, that will make it smoother. So if you put it right up to 10, it's going to be extremely correlated, which will make the function coming out very smooth. Okay, so let's just set it back to 1. We can play more with that later. Okay, so then we're just going to simulate from the implied Gaussian process. So we're just generating from a multivariate normal distribution, basically. So we're going to do that 5 times. So we run down to this figure 1 part. You can see those outputs, right? So these are 5 lines, or 5 realizations of this Gaussian process.
Where are the data points?
So there's no data at the moment. We're just generating from, so what are we generating from there? Well, I guess we're generating a large number of points and then just interpolating them, right? Yeah, so there's no data here. We're just generating curves from there. So I guess really what we've done is generated, say, 10,000 points and then just linked them all up, right, from a big multivariate normal. So if I was to go back and change this tau to, say, 3, then if I do this again, the functions that come out are going to be smoother. So I run down to figure 1, and they're smoother, right? So that's what the length scale parameter is doing. Okay, and then there's also this kind of confidence interval, which is just where you expect the lines to lie.
How do you make the confidence interval?
So that confidence interval is very simple. It's just based on the variance at each point. So it's just it's just like the diagonal of the matrix, of the covariance matrix. So it's only at each point you expect the lines to be within this, like 95% of the time. But because the Gaussian process is correlated, if it goes outside that, it's likely to go outside again because it's correlated for an individual line, an individual realization of the Gaussian process. It's quite likely to go outside multiple times.
So without any data, is that just the scale factor?
Yeah, exactly. It's just the diagonal of the, yeah, I mean, we can see what it is actually plotted here. Actually, we just literally plotted 1.96. So, yeah. Yeah, I guess I should be mentioning that this is how you use GP plots along the way. So if you're not familiar with GDplot, this is, I mean, I don't use it that much, but I have used it a little bit. It's supposed to be kind of convenient because you can plot things in layers, and so you can just add things to your plot. So that's kind of nice, and it remembers the plot. So if I come back here, it gives me figure 1 again, which is good. I don't have to redo whatever I did before. Okay, so now we're going to get some observed data points. So just 10 observed data points. They're just evenly spaced and randomly generated from a normal. So they're the points, 10 points. Okay. Then what happens when you fit the Gaussian process? So the first thing you do is you calculate the covariance matrix of the observed data. And that's what this looks like. Okay, and so you see there's a stronger, most of the correlations, there's only 10, like this is only 10 by 10, right? Because there's only 10 data points. Most of the correlations are not strong. This one is a bit stronger, and if we look at the plot, we can see that empirically it looks stronger, probably. So which 2 points are they? Usually, so this is like the empirical covariance matrix. So the ones that look either strongly negative or strongly positive, I guess it has to be positively correlated here. So it's probably these two, because they're similar values, right? So if you empirically calculate the covariance matrix, then these ones are similar. I guess it's those two. And then what we do is we're then going to, as I said, we're going to predict the value at 100 points, and those points are mainly obviously in between those 10 that we have, right? And so we need the covariance matrix for those. And the first thing we do is we calculate the big matrix. So perhaps I can go back to this slide just to illustrate, just to make it clear. So this slide, so xt2 is what we've observed. We're going to have xt1, and then we want to predict xt1 from xt2. Okay? So the first thing we need to do is construct this big matrix. I mean, obviously we wouldn't actually need to construct it because we just need to do this calculation, but I'm going to construct this big matrix. What does that look like? It looks like this. So these are the parts we're going to predict. They just have the default correlation because nothing has been observed. And these are the observed ones that have whatever the observed correlation is. And then these are these kind of long parts are illustrating the relationship between the observed parts and the prediction parts. So then what we're really interested in is this matrix. This is the correlation for the ones we're predicting. And so that looks like this. So what you will find is that there are some regions, these redder regions, where the variation is higher. And if you look back at the original points, that's because there's no points there, no observed points. So the prediction, it doesn't know what to predict. So there's high variance. So if we see that, we can do the plot, and you'll see. So you see, these are the observed points, and there's very little variation at the, well, zero. It should be zero variation here at the observed points, because the Gaussian process is supposed to go through them. And then away from that, it's non-zero. Okay. Yep. So, and then the colored lines are just multiple realizations. So the lines actually go through these points. If they don't go through the points, it's simply because the plotting is not fine enough.
What is the gray shaded region?
So the gray, the gray region is the 95% confidence interval for the. So you'll see that most of these colored lines, which are realizations of the Gaussian process, lie within that. And so that's what this covariance matrix is showing. It's saying for the predicted values, which are all basically there's 100. This prediction one is for 100 evenly spaced points across here. And when they're in these gray regions, there's a lot of uncertainty. And if they're close to one of the points, there's little uncertainty. So if we do that again, you can see there's a lot of uncertainty at the beginning because there's no points, then there's a point, so there's little uncertainty, then there's more uncertainty, and so this is corresponding to what's happening here. Okay, so in practice you have this on stage 5 now, so on this you have observation uncertainties. So these points are just observed with 0 uncertainty, these black dots, right? But in practice they would have some measurement error. And so that should allow the black line, which is your best fit, to move around a bit, because you don't really, so it doesn't have to exactly go through the point, because maybe that's not the right point. So we're going to add some error of size 0.1, and then we'll do this again. And this is the observed covariance matrix. It looks the same because it is almost. I guess just the diagonal increases, because that's, if you look at the definition, it's the original covariance. This first term is constructed using that kernel, and then we've just added a diagonal matrix which takes into account the observation errors for each point. Okay. So the only thing that's changed in the plot is that the red has got a bit redder, I guess. Okay, and then we're going to do the same as before. So construct the big matrix, which is just down to here. It looks similar. And construct this, which again is similar. I guess there's going to be a bit more variation, and it's not going to reduce to a point when there's an observed value, because if this is my current observed value, if I observe again at that same time, I know this one has measurement error, so I can fluctuate around it, so I don't have to go exactly in the same place. So that's going to happen when we do down to this plot 5. You'll see that there's now some range around the points. Right. So that means we don't have to exactly go through. Yep.
So what's the black?
So the black is the MLE fit to that. Yeah. In fact, presumably. Yeah. Yeah, but you estimated the parameters, right? Where?
But in this simulation, you set the parameters.
Oh yeah, sorry. We know the parameters in this part of the simulation, but later we'll show how to estimate them. In fact, so this is this part, and you can go back to the beginning and increase tau if you're interested to say 3, and then just run it all again, and it should be a smoother function. You can see how that works. So there's various things. So yeah, yeah. So it's a smoother function, right? And because there's more correlation, there's less uncertainty in those gaps, because the observed points are giving us more information, because the correlation is going further, right? The length scale is.
Can you choose tau again?
So tau you should estimate, but in this case we're just fixing it. So
what's a good estimate?
So people do the MLE or something. Yeah. So because the empirical covariance matrix will tell you about what should be the covariance. Right? So what you would do is you would fit it, and then if you want to do prediction, you use your fitted value. Or of course you can do MCR. Yeah. So as I said, the GP fit in R is not amazing, but this is just an illustration. So they have a very simple function, and just going to generate some very simple data. so like this, and then it's going to estimate the parameters of this exponential. So one of the problems with it is that it doesn't allow many kernels. So it only kind of allows this one, which is not ideal. So it actually has a few things, because so it has beta hat, and so if you type help and then GP fit, then it shows you the kernels that it allows. So where is it? So I think it also allows the kernel called a matern kernel.
I'm not sure if the
limitation of
Sorry?
this package is that the range of your input is between 0 and 1.
Yeah, but it also doesn't allow the very many kernels. Like it doesn't allow the periodic kernels.
I'm not sure it does allow anything besides the squared exponential. It might not even allow.
I thought the documentation said it allows a matern kernel, but I haven't used it. So as you can tell, we don't usually use this. But this is maybe if you're just coding something else, it gives you a first check that you're that it is working. Then they have a more complicated example where it's a two-dimensional example, and in fact, I think I skipped the last part of here. Sorry, let me go back. So what I wanted to show you is then it fits and it gives you the confidence interval, that's at least helpful, right? And then, and it gives you the value of the parameter, although I was searching for how it defines the parameter, but I couldn't see it. So, again, this is a two-dimensional example, and it takes a bit longer, and it gives you some parameter estimates, and then you can, if you're trying to predict new values, this is the surface of values it predicts. And then you can also look at the prediction errors, which are these. Yeah, so it has some edge problem. It's not fitting the edge. That's probably because there's no observations there, right? So that's one option. So as I mentioned, maybe if you want to use a package and you're going to do some serious stuff with GPs, maybe go to Python. Otherwise, if you're going to use R, probably code it yourself or find some code, some existing code. Okay.
Yeah, so like one caveat with that package that it's really made to do emulation. So that's why it has kind of not very many kernels and sort of a unique setup.
Yeah. So the first part we were not using that package. We were just like writing everything ourselves. So that's kind of a template for a very simple implementation. If you did need to do that. So yeah. Okay. So that's kind of this first part of code, and then. I'm going to go to the second part called part 2, and just clear the workspace. Are there any questions about part one?
May I ask you one thing? This method is similar to a kernel method.
Yeah, exactly. It is. It's equivalent.
It's equivalent, right?
Yeah.
But if I remember correctly, kernel methods mean that you want to estimate a function, and the function equal to the summation of the linear combination of a kernel.
Yeah. So this is a linear combination. So like, because it does this. This is the estimation.
Yeah.
So if you want to predict x at times t1 from x of t2, it's just like a regression, which is also equivalent to using a kernel, and then it's equivalent.
Because in kernel method, kernel method, how can I say, it's the linear combination of kernel, right?
Yeah.
But they each have a parameter, a parameter to make a linear combination. Do you know? Probably we can talk later.
Yeah, I'm not quite sure.
This means not given the function, you expand this function with the kernel method, with the kernel, right? But the kernel, there is the parameter, there is a variable.
Yeah.
But I don't know how to estimate this variable.
Oh, so if you can, so in the Gaussian process case, it's there's, you can write it as a normal distribution, and then you just do maximum likelihood to find the parameter. Yeah. So maybe there's an equivalent, but the thing about the Gaussian distribution is it only depends on the mean and the covariance. So then you get the probability distribution from that specification. But if you just specify the covariance matrix for some other distribution, it doesn't tell you what the distribution is. So then you can't write down a probability distribution just based on that. You have to make the normality assumption in order to do that. Okay, so this is the second piece of code. So here we're going to load a little data set of some light curves. So there's two things written for estimating the kernel parameters. One is called fast estimate, and the other is called accurate. And so there's some trade-offs that you can see. We're going to use the fast one for now. And so we're going to load some data, which is just this light curve data. I'll do a plot in a second. So it's the bottom is time, and the y-axis is magnitude, so the brightness of the star over time. And then we'd like to kind of fit this with a Gaussian process. Okay, and you see there are measurement errors, and often in astronomy they're very erratic. Again, we're going to predict some points in between. Okay, so now the kernel is this. So the kernel is let's go period square. Yeah, so it's k of, I guess you could say t and s is exp of minus some length scale parameter, and then sine of pi and t minus s. I guess I should delete this. T minus s divided by some period parameter. So that's the period of our oscillation. Did I write that correctly? Yeah. And okay, so this controls the period of the oscillations. And this is like, we had the length scale, this is just the inverse length scale. So I guess before we saw if it was larger, it was smoother. And so now if it's smaller, it's smoother, because we flipped it. Sorry about that. Yeah. So then we're just going to estimate the parameters using this function that we wrote. And then if you want to see them, that's the mean and estimates. That's the estimates of the parameters. So the inverse length scale is estimated to be 2.1. The period is estimated to be 10.3, which if we look at the plot, we can see maybe is reasonable. 10.3 is there. We can kind of hope it goes up and down like that. Estimating the period is generally difficult, so that's why there's a accurate and a inaccurate method. And then this is just constructing the covariance matrix for the values we're going to predict. And hopefully, so now you can see the periodic nature in the covariance function, right? These ones are correlated with ones that are a bit later, and then correlate again, so it's periodic. Okay, so now we're going to draw from the prior distribution quickly, like we did before. So in my presentation, I gave a quasi-periodic kernel. And the reason is, maybe you can't tell exactly from here, but these functions, these realizations of the Gaussian process are exactly periodic. They're not sort of periodic, they exactly repeat. And so that's something that's not realistic in many applications, so that's why you might want a quasi-periodic thing. Again, we can just do this confidence interval for where we expect them to lie. Okay, so that's just from the prior. Then we have some actual observations. And this is the empirical covariance. We're still exploiting this, but the, are we? Yeah, because we're just calculating. Yeah, we're using the kernel to calculate, but this is for the observed data, what the covariance is. So they're not spaced evenly, so and they have different variances. So there's, and then the big matrix, which again is this one, is this. So the main part is the part we're trying to predict, and the other part is the observed part, and then these are the correlations between what we have observed and what we're going to predict. And so the final prediction covariance matrix looks like. So when you condition on the observed data, you get this. So I guess it has this structure because it doesn't only matter whether you have a point near it. It rather matters whether you have a point in the same phase, because it's a periodic function. So if it's in this, if you have a point in the same phase, it's okay. If you don't, then whenever you try to predict at that point, it will be a problem. So it has this kind of repeating pattern. So actually you can predict very well. And as you see, there's the repeating pattern I mentioned. So because there's uncertainty here, there's also uncertainty here. Because if there was a point here, then I would know what the function was here because it's periodic. But because seeing as there's uncertainty here, there must be uncertainty here and here. Yeah? Okay. And then one thing you often do with light curves is you just plot the phase plot. So only you do a modulo transformation, modulo the period, so it looks like. you just put all the points on a single oscillation by doing a modulo thing, and you can see the shape better. Okay. So I'm not going to go through any more of this one. You can, but there are other light curves. So at the top, I selected Cepheid 1. It's actually a Cepheid light curve. You can choose other, like 2. I think there's 6. But I think I put 2 of them are not really Cepheids because I was designing something, and so if you want to work out which ones are not Cepheids, that's. But this one is a real Cepheid. Okay. So, yeah, then I just wanted to finish by saying that Gaussian process can also be implemented in Stan. So the Stan kind of repository on GitHub is here. No, because I turned my internet off. It will be here. And they have like various examples and have tried various things. So I took one of their functions and just tried it out. So Stan is a package for implementing HMC, Hamiltonian Monte Carlo, which is like MCMC basically. But it uses Hamiltonian mechanics to help it decide where to sample. So it can be more efficient than just MCMC without anything else. It uses the derivatives of the target, which help. So the Stan code looks like this. So Stan is very convenient. You just write down your model and what your data is. So here the model is like a multivariate normal distribution. So you just write that and some priors, and you tell it what data you're going to input, and then you just basically click run, and it creates an MCMC Hamiltonian sampler for you, which is very nice and saves you a lot of time. So here, just generating some kind of ridiculous data. And actually, I've just realized, I'm going to run this on a different computer because this computer, it doesn't run Stan. Sorry, 1 second. Okay, so here is the code. So I've just generated some random data, and I'm mainly going to show you how it fits the parameters rather than, it's just going to fit a mess to this, right, if it was fitting a line. But I just want to show that it looks for the parameters and so on. So it's now constructing the sampler. And then I said do 3 chains, MCMC chains, or HMC chains with 2,000 iterations. And so it prints, and it's very fast because there's not much data. So like 1 chain is already complete. It's going to run another chain at some time. So the model I'm running, you can see the kernel in here. There's a bit of Stan language which you may not be able to read, but this is just the squared exponential kernel. Okay, so it's just the top one. There's x and xi and xj squared, and then some length scale parameter. And I think they also add in some noise, some additional noise, like the measurement error. that we saw. That was the wrong thing to click. So now it will have finished, presumably. Yeah. Okay. So then you can look at the fit, and it tells you some information. I don't know if I can actually make this bigger, which is a little annoying. So yeah, I doubt you can read this, but it tells you kind of the mean posterior value, the standard error, and then some quantiles. And it also gives you some diagnostics.
So are these hyperparameters?
So the first one, what is the first one? So the second one is the length scale parameter. The third one is the nugget, the noise parameter, the measurement error. And yeah, the first one you have to look. Oh yeah, so it's just the scale. The scale for so this one can have an additional parameter, this covariance matrix, because this can only go, it can only go to 1, right? Because if the difference is 0, then this would be 1. But so you might want to scale out the front. So that's probably what the eta squared is. And so then it also does nice. Well, these are just confidence intervals for what the values of the parameters are. And you can do these kind of plots to look at the correlations between the parameters. So this is the first parameter and the correlations with the other parameters, the second parameter and the correlations. Yeah, so I just wanted to show a histogram of. So this is rho. This is one of the parameters, and yeah. So you basically get out a big matrix with all the posterior draws from the sampler. That's the matrix. Okay, so that's kind of handy. Yeah, so that's basically all I wanted to say. If I just come back to here, there are a few other resources that we may have already mentioned, but there's just a few things. So as I said, there's some Python libraries, and if you search for Python tutorials online, they have those those Jupyter, I guess they are Jupyter notebooks now, so that you can like run the code through. So it's kind of very easy to follow. Yeah, and there's Neil Lawrence, who does lots of Gaussian process stuff, has lectures. Okay, so I guess we can stop there. Questions?
Yeah. So with this stand code, what do you have to supply it? I guess, is it smart enough that if you give it the kernel, it can give you all like the matrices you need, or do you still have to give those to stand?
So
essentially give it as like a multivariate normal?
Yeah, so what as you see, this is there's a stand run code, which was this. I just basically said run. This line said run. I just gave it inputs, data, and said run. But the stand coding is simply, you specify the model. It comes in a few stages. First, you tell it what data you're going to give it, just as you would in many programming languages. Then you tell it what parameters you're going to give it. And lastly, you tell it what the model is. So in the telling it what the model is, you specify how the covariance matrix is constructed from the times that you're inputting, the data times or observation times. But you see, but you can specify whatever you want, right? So yeah, you have to write down what the model is, but then it will construct the sampler for you. Yeah. Yep.
Do you have any recommendation when you use different kernel? For example, in this case, when you want to use a Gaussian kernel, or when you want to use a quasi?
So the second one is a periodic one, so that will give you functions that are strictly periodic.
Okay, it means that the estimation function will be periodic.
Yes, and what you can do is multiply these two together, and then you get something called quasi-periodic. So it has some periodic behavior, but that periodic behavior fades over time, determined by the second, the top one, which is.
So it means that it's really depend on the data. If your data is periodic, so you will use the second one. But if your data is smooth, you want to use the first one.
Yeah. So it's yeah, exactly. So the only thing you're specifying is the covariance matrix. So hopefully you know something about the covariance. Otherwise, it's very difficult, right? If you don't know anything about the covariance, maybe you just use the exponential one, the squared exponential one, and if it's periodic, it will still model it. It just won't know that it's periodic, so it will lose some information.
And I have one more question.
Yeah.
So this method, I don't know about statistics so much, but this method called parametric method.
This is a non-parametric method because you're not telling it, because the function depends on what the data looks like the function that comes out, right?
But you have to use the kernel, so how can...
Yeah, so that, I mean, but that's always the case, right? There's never such thing as a model without any parameters. There are always parameters.
Yeah, because in optimization, I mean the one that I use in deterministic, usually we define a function on a space. We say that, okay, let's say if you want to have a smooth function, we just say that, okay, the function stay on the L2 space.
Yeah.
Or on some space. We don't have any form like this. And I don't know, this one called non-parametric or parametric.
If you do just the L.
This means that only assume the function stay on some space. We don't have any formula, only assume.
Well, that's non-parametric then, I think, yeah. That's
so this one probably is the main but anyway, it's fine.
Yeah, so this can, I think you can view this as somewhat semi-parametric.
This one, right? Semi-parametric?
Yeah.
Yeah, I also think so because you have to define a kernel.
Yeah. Yeah. Okay.
I was thinking sometimes when people say non-parametric, they also just mean that you're not parameterizing like the function that takes like the inputs to the outputs. You're parameterizing this other thing that's sort of like is an approximation, but.
Yeah, so Gaussian process can also be viewed as a prior distribution for functions. So y equals f of x. F is unknown, but you say f is a Gaussian, the prior for f is a Gaussian process. So it's an unknown function that you're giving. So in that case, of course, the Gaussian process has parameters, but the function that you want to know doesn't have parameters, right? Because you're just giving it a prior, and you're not assuming anything else.
But if you assume the prior, if you assume the prior as a Gaussian, so where is the kernel coming? I mean, where does the kernel come in?
Because that shapes your. Of course, your prior has some shape. It's not just.
Okay.
Yeah.
Understood. Yeah. So this one is the shape of the kernel, right?
Yeah. It kind of like restricts the kind of things, the functions that are allowed by your prior. Yeah. Okay. So I guess we'll meet next week. So what's next week? Oh, okay. Sorry, we won't. So next week is spring break, and then after there'll be something else. Yeah. I'm not sure what's on the schedule. Okay. Thanks.